All right, we continue on with finding volumes of stuff using integration. And let's recall what we did last time. We found the volume under some surface f of xy equals z on a region R that was AB cross CD, where AB is on the x-axis and CD is on the y-axis. Okay, now we're going to extend this to non-rectangular regions. R, and it winds out being a pretty cool little algorithm. So we'll start with a problem, an example, and then build the theory from there. So here's our example. We want to find the volume of the prism whose base is bounded by, and this gives us our R on the x-axis, the line x equal 1 and the line y equals x. The top of the prism is the plane z equals 3 minus x minus y. All right, so this is really similar to what we did, but now our base turns out to be non-square or non-rectangular. So let's get a nice picture up here. Try and leave all that up there. So I'm going to put 1 out here on the x-axis. So here's the line x equal 1. On my best work there. Let's see here. The line x equal 1. So, and then we have the, what are the other ones? X-axis, so it's this guy. And the line y equals x, which goes like this. So here's our region R. And there's a line, there's the point 1 on the y-axis. Z is going to go up there. And so x and y are 0, z is 3. If x is 1 and z is 0, then z turns out to be 2. So put that about right there. And if they're both 1, it becomes 1. And sure enough, it's a prism. Okay, so if you went at this blindly, you'd go, all right, the volume is going to be the double interval, and we're going to have x and y here. F of xy dx dy. So the whole game becomes figuring out what to put as your limits of integration. Okay, so well, this is the way to do it. So what you want to do, step 1, is to moving away from the origin. So you're gonna draw a ray that intersects the region here and exits it here. Okay. And so this is going to be your boundary y equals x. And this is going to be your boundary x equal 1. So first you find these boundaries, and you go, okay, I'm gonna come in this way, enter here, and exit here. And so this is your lower bound. That's your upper bound. So let's put those in there. The lower bound is x equal y, and your upper bound is x equal 1. And then we put the function in here. And since these are functions of x, we go, this is dx. Okay. And then we say, to scratch out all of these going this way, y needs to run from 0 to 1. dy. Okay. Let me move this up just a little bit. There we go. All right, different color. Let's do this in purple. I could have also come in this way and intersected here and here. And so this intersection would have been what? Y equals 0 to y equals x. F of x, y, dy. And then x runs from 0 to 1. Dx. And so that changes the order of integration, but because we're finding volume, I should get the exact same number. And you don't have to do this twice, but so let's go ahead and do this. So volume equals this guy, and this equals the integral from x equals 0 to 1, y equals 0 to x, and this equals the integral. Integrate with respect to y, you get 3y minus xy minus y squared over 2 evaluated from 0 to x. Okay. And so this becomes x goes from 0 to 1. You plug in x, you get 3x minus x squared minus x squared over 2 minus 0. Okay. And so now you get 3x integrate again, you get 3x squared over 2 minus x cubed over 6 from x equals 0 to 1, which is 3/2 minus 1/6. I made an error. Let me back up here. X squared minus x squared over 2 is minus 3x squared. Just caught that. It happens. Right? Yes. So now when you integrate, you get 3x squared over 2 minus x cubed over 2. And x goes from 0 to 1. So you get 3/2 minus 1/2, and you get 1. All right, that was fun. And you could do it the other way as well. I'll give you the same answer because volume is volume. So let's generalize this. Okay, ooh, go back to black here. So the general algorithm. So 1, sketch R in the X, Y plane. 2, then sketch a vertical line. Through R, increasing with respect to Y. So if we had a little region over here, it would be going this way, right? And this lower bound is Y is F1 of X, and this upper bound is Y equals F2 of X, right? And so the volume is going to be, what's going to be the general derivative with respect to area A, which in this case is, I'm going to let X be some constant A to B, and Y is going to be F1 of X to F2 of X, and we go F of XY dy dx. Okay, and this also works horizontally, right? So you'd sketch a vertical line with respect to X here instead of Y, and then your bounds here would change. So you'd have functions for your first bounds and then constants for your back bounds. Okay. All right, you can also unravel this and do it in reverse. So let's say you're given a double integral. So let's say you're given this integral, and that's a 4x plus 2. Okay. So let's say you're given this integral, and you'd be asked to sketch the region of integration for this integral. Then write it in reverse. And then integrate. And one of the tricks to this game as well is that, of course, the integration is always going to give you the same answer because it's volume. It's also always going to be positive. But sometimes choosing one over the other makes more sense. It's actually less computation. In fact, this one example here above, if you do it flipped, there's a couple more steps. It's just more work, but whatever. All right, so I have this in my notes as guided practice. And so let's do that. You guys do this, and when you come online to see me, hopefully you have this finished. And it's not important now so much for this lecture that you draw the whole volume piece. What is important though is that you have a really good drawing of R. So when you draw an R, you can do it in the XY plane, and it'll help you to understand how this process works. All right, let me give you some homework here before I forget. This is homework 9, part 1. From 15.2, problems 21, 22, 28. Oops, that should be Don't want to get this wrong. 28, 59, and 63. There'll probably be 5 or 6 or 10 more problems before next Monday. So see you in a minute.